So it's a great pleasure for me to introduce Professor Luca Carlone from MIT today to talk about his celebrated work. So in short, Luca is getting Best Paper Award in every conference, and I don't want to comment further. Luca, just go ahead.
Thanks, Naida, for the nice introduction. It's a pleasure to be here and to give this seminar. I'm really excited just to share a little bit of the work that we have been doing, and also getting feedback, and getting into the discussion that we were mentioning with Naida before. So happy to be here. As Naida mentioned, I'm Luca Carlone. I'm an associate professor at MIT, and the plan for today is to tell you about our work on certifiable perception and real-time scene understanding for autonomous systems. And I think a good way to start is just with, by giving credits to the many students, postdocs, collaborators who have been doing essentially the heavy lifting behind the slides that I'm going to present today. So maybe a good way to start is just by telling you, a little bit of an introduction about my lab. At MIT, I'm the director of the Spark Lab. Spark stands for Sensing, Perception, Autonomy, and Robot Kinetics Lab. And we work in the broad area of robotics and autonomous systems, but we have a focus on robot perception and vision-based navigation. Of course, to this audience, you will be familiar with vision-based navigation with perception, but just to make sure we're on the same page, I like using this picture to explain what perception is to my students. So imagine that there is a robot observing the real world with some onboard sensors, for example, cameras, lidars, inertial sensors, and so on. Then perception is the set of algorithms processing the sensor data and building an internal model of the external environment. So I have a very broad definition of perception, and is including problems such as localization, mapping, object detection, pose estimation, object tracking. And in general, you can think about perception as a broad umbrella for challenges in computer vision, signal processing, state estimation, probabilistic inference, machine learning, and more. So my lab is focusing on robot perception and vision-based navigation. And in particular, we have a number of motivating applications. In a nutshell, the motivating applications are applications which are safety critical, high integrity, and highly interactive. And I'm putting here 6 examples taken from some of the projects we have been working on. You're going to see some of these in the upcoming slides. But just to give examples, when I'm talking about safety critical applications, these are applications, for example, like search and rescue. Here, if the robot is failing, or the perception system on the robot is failing, we might fail to find survivors. So we're putting human life at risk. Another example, which everybody will be familiar with, is self-driving cars and autonomous vehicles. Here, if the vision system of the self-driving car fails, the car may crash and kill the passenger, or kill the pedestrian. On the right-hand side, I have an application which is high integrity application. So this is essentially a rocket with some autonomous navigation system. In this case, there is no human on board. In many cases, there is no human on board, but the equipment is very expensive, and we just want to make sure that the algorithms are reliable and are not breaking the equipment. At the bottom here, I have a number of applications that we call highly interactive applications. These might involve interactions among multiple robots, interaction between the robot and the environment, or interaction between robots and humans, okay? So a key motivation behind the work of my lab is to realize that there is still a large gap separating robot perception, what robots are capable of doing, from human perception, what humans are familiar with and are able to do, perception-wise. And I will give you just a couple of examples just to highlight how large this gap can be. So we start with a little bit of a tricky one. I will start by flashing this picture. And as a human, you can spend a few seconds looking at this picture. And you can realize that this picture actually does not picture a car, does not picture a human, but actually the car and the human are painted on top of a white van, okay? So there is a white van here, and there is a sticker, right? And as a human, I can guarantee you that if you spend enough time, looking at this image, you can figure out, that this is a subtle image, but you can figure out what's going on in the image. We can pass this image to a state-of-the-art transformer-based model for robot perception, and this is what we get. What we get is that the robot perception system is detecting the car, is detecting the person. So in other words, the robot is unable to do the complex reasoning behind distinguishing the fact that the person and the car, they're not physically there, but they're stickers on top of a van. Okay, you might say, Luca, this is a little bit of an involved example. Is this does this happen in real life? Well, there are many examples of that are maybe much more straightforward that highlighting failure modes of robot perception today. So one example is from Waymo, is the video that I'm going to play on the left. In this case, there were pranksters, which are the people that you see here wearing stop signs on their t-shirt. And essentially what's happening is that the Waymo self-driving car is confusing these t-shirts for actual stop signs, and they're stopping. Okay, so these humans with just a t-shirt, they're forcing self-driving cars to stop at random places, which is funny. It's something that for humans is a mistake we will never make. On the right-hand side, there is a similar example for a Tesla autopilot. Here, the Tesla autopilot is looking at a truck with a bunch of traffic signs on it. And essentially, the system is not understanding that the traffic lights are on top of the truck, and it's thinking that some of these traffic lights have to be fixed, and they're coming towards the car itself. So it's has a completely incorrect understanding of the world. And indeed, Tesla, for a while, had a lot of issues with this phantom braking issue. Of course, these are just funny examples, but the truth is that robots that have an incorrect perception of the world are bound to make bad mistakes in practice, and these mistakes can be very consequential. So in this slide, I'm going to play a video, which is a little bit disturbing. So just as a heads up, it's a bit of a disturbing video. It's about an accident with a Uber self-driving car back in 2018. So this is a full self-driving car. The safety driver did not pay attention. Essentially, the self-driving car system, the perception system of the self-driving car completely failed to detect the pedestrian and killed the woman crossing the street. This is back 2018. One might say, okay, we had 6 years, now we have a lot of progress, but the truth is that if you look at the self-driving car news, unfortunately, these problems persist. And in particular, if you look at the dates that I have on this slide, these dates are ranging from 2018 to December 2023. And actually, if you look, I Googled this yesterday, but there are examples from the summer of this year. So they're they keep happening, right? And these are examples in which the car is not really understanding the environment and is making bad mistakes that are killing people. So the question is, can we develop better perception algorithms for our robots, for our autonomous systems? And today, what I want to do is to tell you about 2 lines of work that we've been pushing, including scene understanding and how that connects with robust perception, and the idea of certifiable perception algorithms. So I will spend the next part of the talk talking about real-time 3D scene understanding for robust perception. And then this part is going to be fairly high level. Then in the second part of the presentation, I will talk about certifiable algorithms. And if I have time, I will go a little bit deeper on the math of the certifiable algorithms. So the message I want to convey in this part of the presentation is that perception is more than detection. Okay, so most of the current algorithms for perception are doing detection, but human perception is definitely more than detection. And indeed, robust perception requires reasoning in 3D and accounting for context and relations. So this statement should be pretty clear from this example I gave you. If you look at the example on the left-hand side, this one with a car, if I reason in 3D instead of reasoning in 2D, I'm able to understand correctly the scene and understanding there is no car in the scene, but it's just a truck. The right-hand side is a perfect example to understand the importance of context. Okay, if I look at the stop sign, if the stop sign is on a pole at the side of the street, there might be an actual stop sign. If it is on a t-shirt, cannot be a physical stop sign. So next, I'm going to tell you the work we did in enabling reasoning, 3D reasoning for robot perception, as well as accounting for context and relations. We started on this several years ago. The first work we did is what we call Chimera, which is a library for 3D metric semantic mapping, which allows robots to understand the world, again, in 3D. So what Chimera does in terms of input-output is very simple. Let me replay the video. So Chimera is getting camera images as the ones that you get from a typical camera on board of a robot. And in real time is building a metric semantic map. So the map that you see here is a 3D mesh. So the 3D mesh, like, the phases and the vertices of the mesh are describing the shape of the obstacles in the environment. But this is also a semantic map, meaning that the mesh is color-coded with different colors corresponding to different types of objects. For example, light green can be couches, dark green can be walls, gray can be ground. These other type of green can be chairs. So different colors will be different objects, and now the robot is able to understand in real time as it goes. We released this library a while ago, and this was the first CPU-based approach for metric semantic 3D mapping. Since then, we've been doing a lot of work, in particular in collaboration with the Army Research Lab, in which we've been scaling up this capability of enabling 3D scene understanding for robots and metric semantic mapping for robots, including multi-robot systems. So with the Army Research Lab, we've been using, developing this system and deploying them in which there are multiple robots. For example, in this simulation, there are 3 robots. The robots are exploring the environment and are building this 3D map. The 3D map is color-coded with different semantic labels, but also when the robots are meeting each other, they're exchanging information and correcting this map as they go. We've been doing this in simulation. We've been doing this on real systems. One of the experiments I'm most excited about, we did an experiment at MIT last year involving 8 robots, which are the 8 robots that you see here. And we were able to map large portion of the MIT campus. So 8 robots traversing overall around 8 kilometers of trajectories across the MIT campus. Of course, with limited communication, we just have small computers on the robots, as well as limited communication. We just have a standard Wi-Fi network. This was the first approach to perform multi-robot, dense metric semantic mapping, and was best paper on transactional robotics a couple of years ago. After starting with this work on Chimera and building these meshes, these metric semantic maps in the form of a mesh, we quickly realized that the meshes are not enough. Meshes are not enough for scene understanding. And in particular, they're not capturing well relations and context around the robot. For example, imagine that I want to issue a high-level command to my robot. I want to tell the robot, go search for survivors near the fridge in the kitchen. Well, just a mesh will not contain the notion of kitchen, will not contain the concept of kitchen, and also will not contain any information about relations, will not say whether survivors are near the fridge and what it means for the fridge to be in the kitchen. So in other words, meshes are not good to capture context and relations. Therefore, the point here is that we have to develop better representations that are able to understand semantics beyond objects. For example, I have to understand rooms, buildings, humans, very complex type of semantics. And also, we need representations that are able to reason over relations within elements. For example, what it means for the fridge to be in the kitchen. So this kind of insight pushed us to develop a novel map representation, which is what we call a 3D scene graph. The 3D scene graph is what you see on the right-hand side in this slide. Essentially, this is a hierarchical graph-based representation in which at the lowest layer, you have information about the dense geometry of the scene. This is the mesh that we were talking about before. But as you go up in the hierarchy, you are abstracting away dense geometric information into high-level concepts. For example, humans, objects, rooms, buildings, and so on. And there is also a layer which we call places and structures, which is essentially describing the traversable space in the environment, as well as structures in the environment, for example, walls, ceilings, and so on. So we propose this representation. And again, the nice thing about this representation is kind of is hierarchical and contains information at different levels of abstraction, but also it's kind of a graph. So it's kind of nice if you want to do a little bit of more rigorous analysis. And indeed, what we did with this representation is to start investigating fundamental properties of this representation. This representation, scene graph that I'm showing on the right-hand side, again, is organizing things hierarchically as a graph. And we are arguing that it's much better than typical representations and instead are flat. For example, mesh-based representations, or if you're familiar with them, voxel-based representations are just flat representations. And we have been demonstrating that instead hierarchical representations will have much better properties. For example, it's trivial to see that, if you have a graph, we can start capturing relations within things through the edges in the graph. That's trivial to see. We've been showing that if you arrange things hierarchically, you just save a lot of memory because you have to just store minimum amount of information instead of storing a lot of redundant information. But at a more fundamental level, we use a little bit of graph theory to prove that the hierarchical graphs showing up in our representations have low tree width. So if you're not familiar with the tree width, in graph theory, the tree width is a property of a graph. And essentially proving that the graph has low tree width means that the graph is nice if you want to make inference over it. You can make fast inference over graphs with low tree width. So essentially we are showing that this representation are intrinsically well positioned if you want to do fast inference, if you want to reason over the representation. Of course, we didn't spend just lots of time thinking about the properties of this representation. We also developed the first algorithms to build this representation, to build 3D scene graphs on real time. So here you see an early example. This is in simulation. On the left-hand side, you see the camera image collected by the robot. And on the right-hand side, you see the 3D scene graph that we build in real time. So you see that as the robot moves around, without any prior knowledge about the environment, is able to track its own trajectory, is going to identify and understand the labels for the different objects, sink, appliances, and so on, and then is able to reason over the fact that, if a room has a sink, has a fridge, and so on, there must be a kitchen. So essentially it's populating the hierarchy as it goes in a fully autonomous way and in real time. This approach is something that we call Hydra. That's the name of the overall set of algorithms and system that is building a scene graph. And as most of the works that we do in my group, there is an open source implementation on this. Hydra, if you want to download it, you just go on GitHub and you can run it on your side. Again, it's all open source. So this initial example was tailored to indoor environments. And again, when I was describing these hierarchical representations, I was talking about rooms, buildings. I was essentially assuming indoor environments. But then after proposing this, we realized that these representations are actually very powerful also for outdoor environments. And in collaboration again with the Army Research Lab and many other sponsors, we develop extensions of these representations to outdoor environments. So before playing this video, I just want to stress what's challenging in outdoor environments. The first thing that is challenging is that the layers of the graph are less clear. In an indoor environment, it's clear that you might have floors of a building, you might have rooms, you might have buildings themselves, and so on. In outdoor environments, if you are in an urban environment, for example, you might have intersection, blocks, neighborhoods, and so on. If you are in countryside, you might have forest, different type of environments. So it was really unclear, what are the concepts that you really want to see in this scene graph representation. And we didn't want for a human to manually label and to manually design, these for every type of environment. The second challenge is that in outdoors, there is actually way less training data we can use. For indoor environments, there are data sets such as Matterport that you can use for training. For outdoors, of course, there are large-scale databases such as Google Maps, but these are typically do not contain information about objects. So they are essentially, they don't have enough data for training of the kind of semantic information that we put in our 3D scene graphs. So in our contribution that was published a few months ago, on the robotics and automation letters, we show how to combine large language models and logic tensor networks in order to extend the algorithms to construct 3D scene graphs to outdoor environments. And the result is that we can do this, again, we can build these 3D scene graphs in real time for outdoor environments. This is a real problem. So the robot is observing these camera images and is creating the mesh, is isolating different objects, for example, seating, boxes, trees, and so on. And then is performing some reasoning over these objects to conclude that, for example, the robot is traversing a road versus an off-road area. So in a second, you should see the top layer of the hierarchy. And you should see that the robot is able to understand walkway, off-road, in different type of regions the robot is traversing. This kind of a small example, we've been doing this at scale in collaboration with ARL. And this is an experiment we did at West Point actually last year the very large scale experiment, and you can see that the robots, in this case, we use both ground robots and a Boston Dynamics spot robot, are able to go around, traverse kilometers of space, and build this type of hierarchical representations that will understand both the presence of objects as well as these high-level regions, including roads, off-roads, buildings, and so on. And we can do all these in real time at this point. So maybe to wrap up this part of the presentation, is worth saying, okay, now we're able to build these hierarchical representations. So now what? Why do we care about this representation? I argue that they are nice to reason over context and over relations, but why do we need them? And the nice thing is that people over the last few years, both my group and other groups worldwide, they've been finding very good applications and very useful applications of these hierarchical representations to different problems in robotics and autonomous systems. So people have shown that if you do hierarchical path planning over these 3D scene graphs, you can make path planning much faster. You can do much better object search. If you have semantic information over a scene graph, you can speed up communication or reduce communication in multi-robot systems. You can do human motion prediction. And including works from other groups, essentially this representation enable things like task and motion planning, goal navigation, and manipulation. So there's quite a bit you can do if you're able to build these representations in real time, and the list grows. Of course, you can understand that these representations are very useful for human-robot interaction, monitoring, visual question answering, and a bunch of other applications as well. So next, I will switch gear, and I will try to go a little bit deeper on another set of works that we have done. And in particular, we'll talk about certifiable algorithms. I might not get into runtime monitoring, but I will mostly focus on certifiable algorithms. And the main message I want to convey here is that robust perception requires algorithms and systems that can detect and adjust to failures. The example that we gave from the Uber vehicle is just exemplifying what I mean here. We would like for the vehicle to detect there is a failure in the perception system and stop before killing the pedestrian. But of course, these examples go beyond self-driving cars. If you're familiar with the Ingenuity helicopter, you might know that the Ingenuity helicopter stopped working last January. And the reason why is that there was a failure in the vision-based navigation system of the helicopter. The helicopter did not realize that there was the failure, and using incorrect information from the vision system, essentially crashed into the ground. And that was the end of Ingenuity. Okay, so in an ideal world, would have liked to catch the failure early on and avoid the failure altogether, even for these planetary robotics, space exploration application. So before I define what is a certifiable algorithm, I will have to I have to start formalizing the problem a little bit more. And the key observation is that behind the nice videos that I was showing in the first part of the presentation, it turns out that we're solving essentially robust estimation problems. Okay, so where we are doing object pose estimation from point clouds, object pose estimation from images, or even localization and mapping for robots, in the back end of these applications, while they seem very different, we are solving an estimation problem. And this estimation problem actually has a form which is common to all these problems, and is typically formulated as an optimization problem. Okay, so here we want to estimate a variable x. The x might be, for example, the pose of the object we are looking at. And we want to estimate the x by solving an optimization problem. The optimization problem is a function of the measurements that you take of the variable you care about. For example, the yi can be a bunch of detections of points on the car that you want to localize. And you estimate the x by minimizing a residual error, which is measuring how well the x is fitting the measurements. Okay. And then, of course, you might have a bunch of different measurements that you minimize, least squares type of objective. So this is nice and easy. People in robotics and other communities have been studying these problems for a long while. The issue in practice is that in robotics, many of the measurements will be incorrect. Many of these detections are produced by deep learning, for example. So many of the measurements turn out to be outliers, might be detections that you believe are correct, but are not correct. They're not, for example, physically belonging to the car. They're outlier detections. Okay. So the question is how to robustly estimate the X in the presence of many outliers. So people in this audience familiar with estimation might say, look, there is a huge literature going back to the 60s on robust estimation. And this literature essentially is telling us that to gain robustness to outliers, we just have to put a robust loss function. Okay, so instead of minimizing a quadratic loss, we just have to put a function rho. And this function rho, the shape of this function is designed to mitigate the impact of outliers. The issue is that what people in robust statistics didn't tell us is how to solve this optimization problem, because it turns out that this optimization problem for typical choices of rho is probably hard to solve, it's probably intractable to solve. So we'll trivialize the state of the art in robotics and computer vision with two main approaches that people use to solve these problems. The first approach is to use local solvers. You start from an initial guess and essentially do, for example, gradient descent or any local optimization methods. The concern with that is that these approaches are really prone to get stuck in local minima. And local minima correspond to bad solutions for the X, so correspond to bad estimates. People in computer vision really like RANSAC. RANSAC is a sampling-based algorithm to solve these kind of problems. But the issue is that RANSAC will essentially only apply to low-dimensional problems. For example, it will not apply to problems such as localization and mapping. In RANSAC, you can show it very easily that it will fail with high probability. It will fail with high probability if there are too many outliers. And in general, one thing that bothered us when we started this line of work is that both approaches will fail without notice. Both RANSAC and local solvers will give an estimate for the X. This estimate can be completely incorrect, but these approaches will not be able to detect that there is a failure. We'll just give you the estimate. And if you trust that estimate, you are bound to make very bad decisions, okay? So our work has been about saying, can we do better than that? Can we design what we call certifiable algorithms, which not only compute an estimate, but also certify that the estimate is the best possible estimate, is the optimal estimate, or are able to detect failure otherwise. So we decided to study this area of certifiable algorithms, again applied to robust estimation problems arising in robotics and computer vision. So at the end of the day, what we want to do is to compute optimal solutions to this optimization problem. And this optimization problem shows up in many applications, from object pose estimation to SLAM, simultaneous localization and mapping. So if you're able to solve this in a scalable way and robust way, you can essentially unlock a lot of applications for robotics and autonomous systems. So I wish I could give you a single algorithm for a single certifiable algorithm, but the truth is that we really designed a toolbox of certifiable algorithms over the last 6 years. Algorithms based on graph theory to filter out gross outliers from the set of measurements, algorithms based on tricks from optimization theory called graduated non-convexity, and algorithms based on what are called moment relaxations. In this presentation, I will zoom in on the math of moment relaxations, because these are the key tools that are used to certify optimality of the solutions and the estimates we get. So I will try to show you in 3 slides or so what is the mathematical underpinning of what we are doing. So how do we get performance guarantees in robust estimation? Again, the problem is that we want to solve some robust estimation problem, and we want to guarantee that the solution we get is optimal to this problem or detect failures otherwise. Our first insight is that a large set of robust estimation problems, again, this type of problems showing up in robotics, can be formulated as polynomial optimization problems. What are polynomial optimization problems? Nothing scary, it's just an optimization problem in which both the objective and the constraints are real polynomials, are just polynomial functions, okay? So how we do that? Essentially, we picked a long list of typical problems that you face in robotics and computer vision, from calibration to structure from motion to localization and mapping to object pose estimation and so on. We look at the math of this problem, and we can show that you can recast these problems as polynomial optimization. For example, if you're familiar with perception, you might be familiar with the point cloud registration problem, in which you want to match 2 point clouds, PI and QI, and you want to compute the rotation and translation to align these point clouds. If you stare closely enough at this problem, you realize that the objective is a polynomial, is a quadratic function actually with respect to R and T. And if you are a little bit more expert on geometry, you might realize that the constraints that the rotation is a proper rotation is also something that you can express with quadratic equality constraints, which are polynomial as well. Okay, so we take all these problems and we manually show that you can cast them as polynomials. Moreover, we show that if you had a robust loss function in front of these problems, and in particular, you can choose any in this list of 7 robust loss functions, the problem still remains a polynomial. It's a little bit of a higher degree 3 polynomial, but it's still a polynomial. And I will not go into the details of how to show that, but you can look at papers. It's fairly straightforward. So the first insight is that we can recast robust estimation for the problems we care about into polynomial optimization. But so far, this is very elegant, it's a very unifying framework, but we haven't gained much really, because the truth is that polynomial optimization is still hard to solve. You can actually cast as polynomial optimization problems things like mixed integer programming or binary optimization. So this is still a very large and difficult class of problems. So what is the advantage then? The advantage comes with insight number 2, which is that for polynomial optimization problem, there exists a very standard way to relax these problems to a convex semi-definite relaxation. So to relax them to a much easier problem using a tool which is called Lasserre hierarchy of moment relaxations. Okay. So there is a huge literature over the last 20 years, these fairly new things in applied math, but this Lasserre hierarchy of moment relaxation, there has been plenty of work over the last 20 years. I will try to give you a 1-slide summary of what the moment relaxation says. And of course, I will invite you to read more. It's a very powerful tool. And of course, these polynomial optimization problems show up in many different applications, not only in a robot perception. So I will show you how to relax a polynomial optimization problem into a semi-definite program, which is convex, which is easy to solve. So for the sake of this example, for the sake of this slide, I'm assuming that the degree of the polynomials involved in the objective and the constraints is less than 4. That's actually what happens in our problem. So the degree of this polynomial is typically 2 or 3, is definitely less than 4. I will also take the simplifying assumption that the variable x is just a vector of size 2, x1 and x2. That's just for the sake of example. In practice, we solve much larger problems. Okay. So for now, let's assume that we have 2 variables and we have polynomials of degree less than 4. What the moment relaxation tells us is that we have to do 2 things. We have to define a monomial basis. Monomial basis is just a vector which is including all the monomials of degree, in this case up to 2, as a function of our variables. So instead of just x1 and x2, now we have all the monomials function of x1 and x2 up to degree 2. So we have x1 squared, x1 and x2, and x2 squared. So this is just about saying the basic insight of Lasserre is that instead of just solving for x1 and x2, you are solving over a larger space in which you try to compute all the monomials instead of x1 and x2 up to degree 2. And the degree is what is called the order of the relaxation. So you decide what is the degree that you want to use. The second step in deriving the relaxation is to form the moment matrix, which is just the outer product of the monomial basis against this vector, against itself. Really, what you have to understand is that the moment matrix is nothing else than a matrix containing all the monomials that are function of x1 and x2 up to degree 4. Okay. So if you look at the entries of this matrix, there will be x1, x2, there will be the squares of x1, the square of x2, the cross products, and everything from degree 0 to degree 4. Okay. So why do we need to define this moment matrix? Well, the key idea is actually fairly simple. The key idea is that if you have a matrix which contains all the monomial of degree from 0 to 4, you can write any polynomial of degree up to 4 as a linear combination of the entries of this matrix. Okay, so any polynomial of degree up to 4 can be written just as a linear function of this matrix X. So in other words, we can take the P, the H, and the G and just write them as linear function of the X. Okay. This gives us.
Can I ask a quick question?
Sure.
I understand you want to simplify so that the problem can be solved in real time. Completely agree. But as we do simplifications, the approximation error will increase. because the definition simplification means something are being omitted, which is deemed to be unimportant. So the question is, what is the error bound as we go down this road, such that we know the simplification do not create too much uncertainty and cause accident?
Yeah. So I will address this concern, in the next slide. And the beautiful thing that happens here is that, in a nutshell, what happens is that these problems are so special that what I'm calling a relaxation is actually going to produce the optimal solution. So there is a very surprising finding that I think is what's cool about this line of research, which if you select a reasonable degree for this relaxation, you're going to get optimal solutions for the original problem. So you're not approximating anything actually. But I will be a bit more formal about that in the next slide. Okay. What I was getting to in this slide is that by using this moment metrics, you can reformulate the objective and the constraints as linear functions. So we reformulated something that is a very hard problem into something with a bunch of linear objective and linear constraints. There is a catch. We started with a difficult problem, and now I'm telling you that we have a problem with linear functions, as objective and constraints. So what is the catch? The catch is in the structure of the matrix X. The matrix X is not an arbitrary matrix, but is a positive semi-definite rank 1 matrix. Okay, so positive semi-definite is okay. That's a convex constraint. We can force it. Rank 1 is not a convex constraint, so we have to drop it. So the relaxation, the only relaxation that we are making is that we drop the constraint that the solution has to be a rank 1 matrix. Okay, that's the only relaxation that this Lasserre hierarchy is doing. So why do we care about this relaxation? That goes back to the question that was just asked. So far I convinced you hopefully that we can convert a polynomial optimization problem into a semi-definite program. The cool thing is that, again, the problem we started with is very difficult, but the semi-definite program is convex, so can be solved efficiently in polynomial time. But why do we think that this relaxation is a good one? Well, the truth is that the results from Lasserre hierarchy are providing very good foundations for this to be a good relaxation. And the theorem that I'm conveying here, I don't ask you to read it. I will just tell you what are the two bottom lines. The first bottom line is that if you solve the relaxation, and just by coincidence, you get a rank 1 matrix. So the solution X is a matrix. If the matrix has rank 1, then from that solution, you can easily reconstruct an optimal solution, a probably optimal solution to the original problem. Okay. So if you solve the relaxation, get a rank 1 solution, you are done. You got an optimal solution, and that solution is probably optimal. The second thing that is cool about Lasserre hierarchy is that the Lasserre hierarchy is telling you that if you increase the order of the relaxation high enough, you're always going to get rank 1 solutions. Okay, so eventually you're going to have a semi-definite program that is going to solve the original problem. Of course, if the order is too high, the size of the X will explode, right? So it might not be practical. But something that is very interesting in our work is the empirical observation that for our perception problem, the relaxation is exact, meaning that it produces rank 1 solution at the lowest relaxation order. So for fairly small X matrices, we already have optimal solutions and rank 1 solutions. And remains tight even if you do some trick and make the X even smaller. Okay, so as a conclusion, for the first time, you can solve robust estimation problems coming up in robot perception to optimality or compute a suboptimality gap in polynomial time. Of course, there will be corner cases in which the relaxation will fail. That's pretty much by definition that's pretty much like an expected consequence of the fact that we are starting from an NP-hard, an intractable problem. For some of the cases, the relaxation will fail because we don't expect to solve in polynomial time all potential problems. But what we see empirically is that in the vast majority of problems, we solve them in polynomial time, we compute optimal solutions. And when we don't compute optimal solutions, we essentially get a suboptimality gap. We can see how bad is the solution we got. So I will, there's much more to say here, but I will just showcase go back essentially to the application to tell you why these things are making a difference in some of the applications. Here I'm showing the result of applying not only the semi-definite relaxations, but our entire toolbox of certifiable algorithms to different problems. And I'm going to argue that we produce state-of-the-art results across a broad variety of problems. For example, we produce teaser++ for object pose estimation in point clouds. Teaser++ is robust to an impressive 95% of random outliers in the point cloud and is able to run in real time. There is an implementation. Many people are using this at this point. We extended this to the problem of pose shape estimation. Again, we have approaches which are robust to 70 to 90% random outliers, and they're running in real time. And finally, we also have approaches which are can scale up to large-scale problems, high-dimensional problems, such as simultaneous localization and mapping. And here we also are able to show robustness with an impressive number of outliers and performance, which essentially is algorithms that can essentially run in real time. And indeed, these algorithms are included in standard libraries for SLAM, for example, GTSAM, and even MATLAB decided to include some of these algorithms in their navigation toolbox. So they're pretty. Yes,
I appreciate your talk. It's very great. I just said, when you have the 95, that's an average number. Then sometimes you can be 80 and sometimes it can be 100. It's a worst case number or average number, 95.
It's an average number, yeah. And also you have to be careful here because the operating word is random, right? Because if you have...
I understand. I just want to know, this is not a bound, this is an average. If it's an average,
that's correct.
How low has it dropped? The lowest number you have seen, 70% or lower or higher?
The lower bound.
Yeah, the lower bound, because the lower bound means the corner case that could have accident.
Yeah.
So that means the lower bound actually is the worst case. So in the standard safety engineering, you want to look at the lower bound. Otherwise, if you fly millions of hours, you will have a fatal accident. So we want to know the lower bound. So
yeah,
so
it's
but
tricky
if
because
you
it's
don't
too
have
problem
that, that's
dependent.
fine. The second question is, are you compare the 95 average number to the oracle, or you compare with the original hard to solve polynomial? So that gives us information. There's some proof, but every proof has assumptions. The assumptions may or may not hold up in the real world. That's the problem. So there's plenty of European systems. They are proved to be no accident, and then you have fatal accident. The most famous is the Ariane 5. It's proof perfect. It self-explode. What's the problem? They make a fatal assumption, which does not hold. All right. So when we have, I'm no doubt your math is okay, but I'm not quite sure the moment relaxed approximation actually holds up in the complex real world. So I want to know that when you run through this polynomial, again, the same set, what is the difference? Do you have that number?
Yeah, I can show you a bunch of real world applications, but there are many subtleties in your question, which are, if you look for a lower bound, for a percentage of outliers for which the approach is guaranteed to work. First of all, that must be below 50%, because if you have more than 50% outliers, you can always design them to mislead the estimation. So there is no approach that can guarantee robustness to worst case scenarios with more than 50% outliers. But also, that conclusion is very problem dependent. So the mindset that we have here is, rather than having a generic guarantee telling you I will be able to solve all the problems with outliers below 70%, here the mindset is slightly different. Is at runtime, I'm trying to solve this problem. If I'm able to solve it, I will provide a certificate that I was able to solve it. Otherwise, I will detect failure. So it's connecting more to monitoring rather than giving a priori guarantees on the approach. The other thing that might stress.
I understand you. I appreciate your work. I just want to note about sorts of logical consistency. Typically, outliers are infrequent, correct? Any statistical outlier, by definition of outlier, is some ridiculous mistake, or ridiculous value, but it's infrequent. So now, if we care about outlier, actually we care about the bound of those big error spike. If we say if something infrequent, we can ignore it. Why we ignore outliers? Outliers by definition is low frequency. Otherwise, won't call it outlier. So now the question is, we do have low frequency or 60%. Now, it might be enough, but it should be in your analysis if you want to do safety critical analysis. Now, I'm not giving you any hard time. That actually is a standard of certification aircraft. I'm a member in those. No, I'm a member on the National Academy of Sciences Committee on Certifiable Software. But that is the actual standard, not I made it up, try to challenge you.
No, I think that's fair. It's well received. And I think this confusion or this point is also partially because of the terminology. Here, certification, in a sense, is also in a mathematical term, in mathematics, I call this certificate of optimality. But I know that, if you're shooting for certification, the entire system, there are much more complicated considerations than that. And I would argue that here we have, some results, which are specific to robust estimation. But in practical perception system, there is estimation, there is some machine learning module running feature detection or running some semantic segmentation. So perception architecture is much more complicated than this. Here we're seeing we have strong results for a specific problem. I'm not arguing that
I agree the complexity argument. I just want to give a simple example. Boeing making aircraft for a very long time for transport. You only have one case over 30 years. The door broke, the door fly out in the mid-air. The frequency is so low, should we ignore it? Say, come on, Boeing have 30 years, make so many airplanes, fly so many times. It just has one. Let's ignore it. Like, why the whole world makes such a big fuss about the door broke out in the mid-time? Maybe we should give Boeing a pass, not to investigate, because it's just low frequency. It's so low. I don't know any other accident in Boeing's history. The door fly away during mid-flight. So the frequency issue cannot say, okay, if we are not safety critical, doesn't matter. But the standard of safety critical actually requires us to analyze that and say, all right, I don't want to occupy your time. I just said that.
It's fine.
All you said is, I want to minimize average probability. You have done a beautiful job. But if you said for safety critical for flight, actually you have a one sprawl out the door. You get ground and investigate. All right, even no casualties. In that case, nobody died. But it's potentially fatal. All right, so
thanks for the
lower bound has to be identified, note, and analyzed. Doesn't mean that anything it presents is not good. It just says that it shouldn't be put under the rug. Thank you.
These are good points, and actually, it is worth mentioning that outliers, when you're thinking about system level, outliers may be these very rare occurrences, that you get system level, the door blowing out and so on. If you look at the details of the algorithms, outliers are defined as things that do not comply to the essentially the model that's used for estimation. So these numbers I'm throwing in the slide are not uncommon. We have problems which have lots of measurements being outliers, and that's a little bit of a unique thing of perception, or is a unique thing of using machine learning to support perception, because machine learning algorithms might produce a lot of incorrect data at this point. But these points I will receive. So maybe to convince you a little bit more about the real world use of these, and I'm not saying I'm solving I solved the certification problem for perception. We're very far from it. We just had a lot of progress in a narrow problem of robust estimation. Maybe what I want to do in the remaining time is to jump on some applications of these frameworks. I will skip these slides and I will jump just directly into the applications. And I will tell you, just a few projects in which we applied these tools, and they worked out, pretty interesting, pretty well overall. One project that we use these tools in is the DARPA Subterranean Challenge. The DARPA Subterranean Challenge is a competition hosted by DARPA, a few years ago. It finished in 2021. And the goal is pretty much to deploy a team of robots to perform autonomous exploration, and you can think about search and rescue in underground environments. So this is a huge multi-robot mapping challenge in very harsh environments. Environments can be tunnels, as these ones, again, very harsh, or can be kind of subway of urban type of environments. And the goal is for the robots to build a 3D reconstruction, a 3D map of the environment, and localize very precisely objects, for example, survivors, or fire extinguishers, or other objects that the robot cares about. So why do we care about outliers in this problem? The robot has to essentially perform localization and mapping, or what is called SLAM. Why do we care about outliers? Well, in order to tell you why we care about outliers, I would just want to tell you a bit about SLAM. In order to reconstruct the map of the environment, the typical approach is to first reconstruct the trajectory of the robot. So you would try to estimate the trajectory of the robot from the initial time, x1. As the robot goes on, you would estimate the trajectory from initial time to the current time. And we would use that using the sensor data. So for example, the sensor data might tell you that you roughly have a measurement of how much the robot moved from x1 to x2. But there are also machine learning and place recognition tools that can be used to detect, for example, that the part of the scene that the robot is observing at x4 is the same scene, is the same portion of the environment observed at x7. These are what are called loop closures. So there are other measurements that you feed to the optimization problem. And again, the optimization problem will figure out the trajectory of the robot. So where are the outliers coming from? The outliers are coming from the fact that there might be different environments that might look similar. For example, this cave, this tunnel, and this tunnel are completely different tunnels, but up to illumination, they look pretty similar. So essentially, the place recognition module might have a bunch of mistakes and might pass a bunch of incorrect measurements to the optimization. And if you're not careful about that, you might have very bad mistakes. For example, if you solve the optimization problem without outliers, you can optimize the trajectory and get a good estimate of the trajectory, which is this one in blue. If you just have 5 outliers, 5 incorrect measurements, if you run the optimization with a least squares cost, the outliers can completely break the trajectory. And again, the same trajectory with 20 outliers over thousands of measurements might completely destroy your map or your trajectory estimate. Okay, so it's very important in these problems to be robust to outliers. So essentially, in the work we have done, again, we put some robust loss function, and we developed this toolbox of certifiable algorithms to solve this problem in a better way. And as a result, we've been able to solve multi-robot localization and mapping problems, for the DARPA Subterranean Challenge. We are first and second place in 2 out of the 3 events of the competition. And I think the things that are more interesting are the statistics about how well we can estimate the trajectory of the robot. So here, for each row, you have different robots. The first column is about the length of the trajectory. This is 1 kilometer. And this is the error that we commit in estimating the trajectory. So we commit over a trajectory of more than 1 kilometer. We have an error in localizing the robot less than 1 meter. And again, this is an error without any external GPS or any external reference system. It's just the robot using measurement and solving this optimization problem in the presence of many outliers. We've been investigating many other applications. I mentioned this DARPA Subterranean Challenge. We've been also using these ideas for self-driving cars. And in particular, we work with Ford and NVIDIA to deploy some of these algorithms for robust vision-based navigation on the Ford vehicles. And we did some project related to fall detection with NVIDIA. And we also deployed some of our algorithms on a completely different application on terrain relative navigation. And my student was actually pretty lucky in running one of his algorithms on the Blue Origin New Shepard rocket, which is the one that you see here, and was able to demonstrate one of these algorithms on this platform, actually. I will try to wrap up, and maybe I can have just one slide or so, but we are applying these ideas to many other applications. We are in particular trying to understand the connections between certifiable algorithm and self-supervised learning. And we're doing that in collaboration with Symbotic. Symbotic is, if you don't know, the company is actually a robotics company doing warehouse management. And it's a pretty big one. For example, they handle the logistics for Walmart. It's a pretty big company. And we're trying to use some certifiable algorithm and self-supervised learning to support them in handling the packages and so on. Some of our algorithms have been used, or they're envisioned to be used for NASA application, for example, assembly of tall lunar towers. And on our side, we've been also investigating a little bit more fun applications of perception algorithm for pose estimation. And in particular, we have looked into ideal manipulation and high-speed grasping. And we've developed, for example, this platform, which can detect the object using our perception algorithms and can grasp them like at high speed. So to wrap up this presentation, I will just say that, as I mentioned before, is that we made some interesting progress, both in building these hierarchical representations and 3D scene graphs, as well as developing this idea of certifiable algorithms for robust estimation. But the truth is that there is still a large gap between robot perception and human perception. System level certification is a huge problem. Certification of machine learning components is a huge problem. And my group is really trying to push in all these topics. And the ideal vision is to have systems that can navigate seamlessly robustly in complex environments. And I typically showing this video, which is just a computer animation. It's not something that you can physically do right now, but it's well demonstrating the type of capabilities that you are shooting for. So in this video, again, this is a computer rendering. You have drones which are navigating in complex indoor environments. They're just using onboard vision, onboard sensors, onboard compute, and they're able to do impressive feats. They're able to avoid obstacles, interact with the environment in a very complex way, interact with each other without colliding, and really show a deep, complex understanding of what's going on and very sophisticated perception abilities. We are not there yet. My group is going to push on these topics for the next several years. But the truth is that if you're able to enable these perception capabilities, we can really enable a broad variety of applications, ranging from search and rescue and disaster response, precision agriculture. These are the same technology that will power self-driving cars as safer self-driving cars, as well as the same technology that will enable vision-based, for example, space exploration to the moon and beyond. And with that, I will thank you for your attention. I also will thank the sponsor for supporting this work, and I'm happy to take questions if there are any. Thank you.
Thank you for a very impressive presentation. And let's see if there are more questions and let you go for your lunch.
Luca, thanks for the great talk. Enjoyed it. Quick question about the second part of what you presented. So I see it's like a runtime monitoring application is maybe the first thing to think about. So can you say a bit more about what happens when there is a distribution shift on where the data was collected and where the system is deployed?
Yeah, so there's much more to say about that. That's a good question. You have to think, when you think about the perception system, typically you think that there is a front end and a back end of the perception system. The front end is typically machine learning powered and is doing some feature detection. For example, in the front end, if you want to detect this object here, the front end will be a machine learning method that will detect features in the image. And the back end instead is using the features or the measurements to perform robust estimation, which is what I covered in this presentation. So you can imagine that we have a lot of progress in the back end, but in this presentation, I haven't touched at all on the front end. And actually your work probably is covering much more about front end machine learning bit. The result of a domain shift is that the front end will be more out of distribution and will start producing more outliers. So what will happen here is that the front end will produce many more outliers. The back end, to some point, will be able to keep up, but at some point, it will be just too many outliers, or maybe 100% outliers for which the back end cannot do anything, right? And that's why I'm insisting so much that understanding safety. Safety, we keep saying, is a system level property. Here, I'm just providing performance guarantees for a specific module in the architecture. If you want to draw connection between these guarantees and system level safety, you have to start understanding how the modules are chained together. You cannot do that in isolation here. I hope I answered. Yeah.
More questions, Lena?
Cheyenne, when I talk about system level, also implies reasoning over perceptions, not only perception failures, but how they cascade on overall system, failures. And that connects pretty well to your work in which you're thinking about task-aware, your task-driven type of failure analysis, which is very relevant.
Okay. I have many more things, but I'll let others talk. Yeah, thank you. Thanks for the answer.
Thank you for a very interesting and impressive presentation. I go back to what Professor Shah also asked. tied to safety critical systems, and I was wondering if you have a handle on how the estimation, the suboptimal estimation that ends up giving the optimal solution, how do they converge? Because it's nonlinear. And so I imagine if you have a lot of runs, you may be able to get a numerical measure, but is there some exploration in that direction in your lab? Because that could make the algorithms more applicable to safety critical systems. If that, and the question, another question that I have is, how is the hierarchy defined before you set up the problem? Are you using Lasserre's hierarchy throughout, or how is that done?
Yeah, these are great questions. I think that the first point is about getting pretty much a priori guarantees. Instead of saying we observe that this works well, is about saying let's define what is the regime in which this is guaranteed to work. Is that fair? Like a fair summary of the first part of the question?
Okay,
I can guarantee, for example, that
how much prior knowledge do you have to define that? Is I mean, yes, I agree with you, but is that limiting?
No, the question, yeah. I mean, the answer is twofold. Like, first of all, the a priori analysis, we have that in very limited cases because it's extremely hard.
Yes,
the issue that comes up, like in these problems, is that, and that's like a general observation, an empirical observation, is that in average we can solve like this problem pretty well, but there are the corner cases which are extremely hard both to solve and to analyze. So we tried analyzing some specific problems, but essentially our solution here is more practical. It's about saying the analysis is never going to be comprehensive, just because we know that there are going to be assumptions, and the analysis are per se for this problem. We tried. Is about saying I'm happy actually if I can solve 99% of the problems to optimality, and if in the 1% that fails, I'm able to detect that failure, I'm happy with that. So that's the framework. But I cannot claim that right now we have a priori guarantees for, this is a very general theorem I'm showing. We do not have
yeah.
And the second part of the question, I think was about the hierarchy. Yeah, so for the hierarchy, just to clarify, this is, are you talking about the hierarchy here or the hierarchy in the second part of the presentation, like in the part before?
I think both. I'm curious whether you're using the same tool or how it is in the first part. Here, it's clearer because you define the constraints, the degree, and so forth. But I was wondering whether this was expandable to defining a hierarchy in the first part. That's all.
Yeah, these are very different right now. Like, hopefully there will be some connection, but right now they're very different. And right now, like, the hierarchy here is induced by the order. So again, if I say the order of the relaxation is 2, I have all the polynomials of all the monomials of degree 2. If I set this to be 4, I have all the monomials of degree 4. And essentially there is a sequence of relaxations, which is the hierarchy, what is called the hierarchy. And the property is that the higher the order, the better the relaxation. So this is a hierarchy of increasingly better relaxations. The catch is that if you go too up in the order, the problem becomes very difficult, very large to solve. So it becomes slower essentially. Sure. But here, just the only thing that you have to understand about the hierarchy is essentially what is the order. Larger order of the relaxation will have more monomials, it will have better relaxations, but will be more expensive to solve. Sure. That's it. Yeah. In the second part of the presentation, instead, the hierarchy is more dictated by the semantics. And the basic idea there is that the hierarchy is describing inclusion relations. For example, objects are included in rooms are included in buildings. So essentially with that type, the type of relations that we capture are a little bit enforcing what is the natural hierarchy that you would consider. At the same time, the idea of scene graphs is fairly general. So you can, we're focusing a lot on spatial relations and inclusion relations, but you can readjust the representation to capture different type of relations. And people in computer vision do that a lot, actually. These representations are very useful for robotics. People in vision, they tend to have more different type of relations, because I think more about vision question answering and applications which are different from robotics.
Okay, thank you very much.
Thank you. Yeah.